All right, I've got 12:01, so we'll start with the introduction here as folks might be still trickling in. First, welcome and thank you all for joining us over your lunch hour, if that's the case, to learn about the power of predictive analytics. This is part of our Inspire Success webinar series out of the Sender School here at the College of St. Scholastica, and this is aligned well with the applied data analytics program that exists here. And we're fortunate to have Dr. Brandon Olson with us to present on the future, how to anticipate the future using those predictive analytics. I know that this will be an excellent presentation. We'll be distributing a copy of the recording afterward, along with the message from Joe Rembowitz, who is our admissions counselor. And with that, I'll turn it over to Brandon.
Great. Thank you, Eric. And as Eric mentioned too, that this is highlights one of the courses in our Master of Science in Applied Data Analytics. We have an Applications in Data Analytics where we cover predictive analytics. And I think Eric's going to put a link to our CSS website that highlights all of our graduate programs. And then there's a link to our certificate programs as well, just in case you're interested. But with that, we're going to talk today about predictive analytics. My talk is called Anticipate the Future Using the Power of Predictive Analytics. So what I want to cover today, my learning outcomes here, I want you to be able to explain the purpose for each form of data analytics, describe the four most common types of prescriptive analytics, be able to determine the process for conducting a predictive analytics study, be able to evaluate predictive models, and to apply predictive models to determine future measures. So this is not going to be so much the hands-on how to build. I mean, that we can't do that in an hour. This is going to give you an overview of data analytics and in particular predictive analytics. So what we're going to cover today is I'm going to begin by talking about the different forms of data analytics, differentiate between supervised and unsupervised learning, walk you through the predictive modeling process, and then begin the process by looking at what's called exploratory data analysis. And we're covering this because that's really key to doing any type of analytic study. And then talk about the four most common forms of predictive analytics, the four most common types of models. They are regression, classification, survival, and time series. So that's what we're going to cover in the next hour. So that's a lot of material to cover. So again, this is going to be pretty high level just to pique your interest and kind of show you what predictive analytics can do. So first, as a background, I want to talk about the different forms of data analytics. So there's four different forms of data analytics: descriptive, diagnostic, predictive, and prescriptive. So descriptive analytics, this is going to answer the question, what happened? And these are going to be the questions that focus on summarizing past events to provide insights into what has happened. And the answers to these questions can be used as the foundation for further analysis in predictive analytics. So this is really going to be using historical data to identify trends and relationships. So it's looking at the past, what happened, be able to describe what happened. And I'll show you some examples on the next slide. Next, we look at diagnostic and analytics. So this is going to be able to investigate the reasons behind certain outcomes or trends. And so these questions are really aimed to uncover the underlying causes or correlations that explain why certain events occurred. And then our answers to the questions that we ask in a diagnostic analytics, they're going to be able to provide deeper insights into the business operations and outcomes, and be able to, we can answer these questions to help to identify the variables that we can use in predictive analytics. So when we do a predictive analytics study, we most likely are going to begin by looking at descriptive and diagnostic analytics to help us understand the variables and maybe the contributing factor to predicting. So then predictive analytics, as the name implies, we're asking what will happen. And this is going to be forecasting the future events based on historical data. And so these questions use historical data and patterns and statistical models to make informed predictions about future outcomes. And then the answer to the questions for this type of analytics is going to help the organizations plan and strategize effectively in anticipation of the future. Therefore, that was the subtitle for this talk's title. And then prescriptive analytics. So this is answering the question of what should we do? And so this is where we recommend actions to achieve a desired outcome based on the analysis of our data. And these questions are really designed to provide decision-making by suggesting actionable strategies and to optimize better outcomes or certain outcomes that we're looking for. And that is going to use more machine learning, AI technologies. And we're not going to cover that today, but that's the highest form. And you can see based off the plot here that those, as we go to the right, those are higher complexity, but higher value. So they take more work to get answers to and much more sophistication as you move along that complexity scale. But the value to the organization or to your questions are greater. So some examples of the types of questions that we would ask for each of these forms of analytics. So first, for descriptive analytics, we could answer questions like, what was the total revenue generated last quarter? How many units of each product were sold last month? Or how has customer engagement changed over the past year? So again, we're looking at past data and trying to figure out what happened so we can understand what happened. Next, diagnostic analytics. Here, we're going to ask questions of why did it happen? So we're looking at a deeper understanding. So we could ask questions like, why did sales decline in the last quarter despite an increase in marketing spend? What factors contributed to the sudden surge in web traffic last month? Or why certain products are underperforming in specific regions? So this is answering, well, why did it happen? So we're taking what happened and now going and asking the question of why did that happen? And part of the outcome of the diagnostic analytics is to see if there's any relationships. Like, do we see a relationship with sales and marketing spend? Or do we see a relationship between products in certain regions? And those are variables then that we can use in our predictive studies. So speaking of predictive studies, so some predictive questions will be questions such that which products are likely to see a surge in sales during the upcoming holiday season? How will changes in the interest rate affect the housing market trends next year? Or what are the projected revenue figures for the next fiscal year based off of current trends? So these are all taking past performance and trying to predict the future, kind of stock market or kind of also weather forecasting. Those are different forms of predictive analytics. And then finally, prescriptive analytics. This is going to be asking questions such as, given the current market trends, what pricing strategy should we adopt to maximize profits? So we've got some type of objective we're trying to reach. So how do we use these different variables to maximize or perhaps minimize an outcome variable? Now, the question would be, which marketing channels should we invest in to optimize our return on investment? Or how can we alter our product schedule to increase efficiency and reduce costs? So those are more of like, what should we do? So some type of actions that we can take. What are the actions we can take to optimize or minimize the output variable? So today we're going to be going through descriptive, really to do predictive analysis, we typically go through a descriptive and diagnostic analysis in order to get to our predictive studies. We're going to focus on this predictive analysis today. Most organizations are doing descriptive and diagnostic. It takes a little bit more sophistication to do predictive. So the tools are different than what you would use for descriptive or diagnostic analysis. So speaking of tools, everybody can do analysis with your spreadsheets. There's a lot of descriptive and diagnostic tool or analysis that you can do in Excel. And since the ubiquity of Excel is a great tool to get started with to do data analytics. If organizations are going to be a bit more serious about it, they're going to invest in some other tools, such as getting access directly to the database using SQL. That's one way to do some analysis. And again, that's probably more the descriptive and diagnostic levels. More sophisticated predictive and prescriptive studies are going to be done through R or Python. So those are kind of easier programming / scripting languages that you use. And I'll show you some examples of things done in R in this presentation. but there's also more user-friendly tools that organizations use for doing descriptive and diagnostic analysis, and that would be Tableau or Power BI, and you've probably heard of these. They are they're very powerful in terms of being able to do descriptive and diagnostic analysis, but they do lack more the sophistication in the libraries to do more complex analysis. So but they are great tools, and you can create very powerful visualizations pretty quickly. All right. Now, next, I want to introduce you to the different forms of learning. So when we're predicting, we have to learn from our data, and that's true for prescriptive analysis as well. You're making, making decisions based on past data, and so we have to learn from that data. So there's two different forms. The different forms are supervised learning and unsupervised learning. So first, let's begin with supervised learning. So this would be an example of supervised learning. So if we wanted to be able to predict a student's final grade based off of their midterm scores, the number of hours per week that they report studying, and their classroom attendance, we can look at past data. And because it's supervised, that means we have labeled data. So we can take a look at our past data where we know the answer. We know our dependent variable, which is final grade in this case. So we can take a look at the contributing variables or independent variables, midterm scores, hours studying a week, and a classroom attendance to be able to build a model to predict that final grade. So based on this, we can build a model, we can test that model, but then what we can do is with that model, we can take new data where we don't know the final grade and be able to predict what that final grade will be. So the model was built on having that what's called labeled data, or in other words, we have the answer for data. We can build a model that's going to predict that answer, and we can verify how well we're able to predict it. Then once that model's in place, now we can use new data that does not have the answer, that's unlabeled, to be able to predict what that final grade will be in this case. Now, different form of learning is unsupervised learning. So this means that we don't have the answer. We have a bunch of data, but we don't have the final grade. So we can still build a model, but not very easily. So this would be where we're going to just use the pattern. We've got lots of data, and we're going to look at the patterns to be able to come up with some insight without any explicit guidance or instructions, so that we don't know what the final grade is, but we can perhaps be able to classify, or we could use actually what's called machine learning to be able to predict that unlabeled data. So in this case, unsupervised means we don't have the answer, but we can still build models that's going to be able to estimate that answer. And again, that's using machine learning to be able to study that data, to be able to make those predictions of what the final grade should be. But both unsupervised and supervised learning, it's not guaranteed. We could see models that might be 80% accurate, and that's pretty good. So keep in mind, when you're doing predictive analytics, we don't know the future. We're trying to predict it to a certain degree of accuracy. And that degree of accuracy is going to be important when we evaluate our models. But just know that it's not guaranteeing a precise answer. It's not guaranteeing a 100% accurate answer. All right, so let's take a look at the process now. So to be able to do predictive modeling, there's a series of steps that we need to follow to make sure that we know what we're doing, and we're going to come up with answers that are actually answers to solve a problem. So, the data analytics has been around for quite some time, and what we call data analytics today is really based on what was called data mining in the past. So that's mining data to discover new information. And actually, that's probably more of a data science term now. We call it data science. So, but this high-level methodology called CRISP-DM, this process was established decades ago, but it's called the cross-industry standard process for data mining. In other words, it's a high-level process for doing data science. And it begins with and this is really important though, is understanding the business and the data. So you have to understand the business rules so that you know what the data means. So begin an analysis by understanding the business, what the rules are. And I wish this had this in here, but the problem that you're trying to solve. Why are you doing this data study? You should understand what the problem is. And then from there, you should be able to ask questions of the data where those answers are going to produce some type of action-oriented result that's going to go address that business problem. With that, though, then you understand the business and understand the data. And next, after you have that understanding, you do data preparation. We have to modify, filter, clean our data, maybe sometimes even transform the data to get it in a format that we can use for analysis. And I want to make sure I emphasize that this is not a small step. I hear many estimates. I was at a conference last week. They actually said 60 to 80% of your time is going to be spent doing data preparation. I often hear that 80% rule. So it is a majority of your time when conducting data analysis is getting that data ready for analysis. In other words, the analysis is probably the easy part. Getting that data ready and getting good data ready for your analysis, that takes some time and but if your organization already has like data warehouses or data marts, that means that they've done a lot of data preparation in advance. So some of that work is going to be done for you, but it still may not be enough. You might have other data preparation to do. If you're working with raw data, you're going to have more data preparation to do. Once we have that data preparation complete, then we can go ahead and do data modeling. We can start building our models. So here's where we take our data and we know the answer that we're going to try to ask. We've identified what type of model we need to build. So we go ahead and build that model. And then we evaluate that model. And we can look at if we're doing predictive, we can take a look at how close were we to the right answer. And if we're off, then we can go back, see what we missed on better understand the data business and the data, go through the cycle again until we get to a model where we're happy with it, where we've selected the right predictive variables, we've selected the correct model to use on the data, where we get something that will actually predict. And then from there, we can deploy that either that model into production or that report into production or dashboard, whatever, so that people can begin using it. So this is what the overall process looks like. Now, specific to predictive modeling, we follow something similar, but this is kind of the language of predictive modeling, where we have to go collect the data. So it's not always just pulling it from a database. We might have to collect multiple sources of data, and whether it be from our databases, other external sources. David Mark, a couple of weeks ago, did a webinar on public data sets. So sometimes you're going to be using data like that to be able to include in your analysis. So it's not always just one data set. So we go get the data, clean and transform it. Again, that's maybe up to 80% of your time doing that. Next, then what we do is an exploratory data analysis. And I'll get to that in a little bit, but that's going to be getting a better understanding of the data and maybe some relationships among the data. So that is an important step, becoming very familiar with the data so that you could do something with it. And from there, we know what variables that we want to use, what are our predictive variables, and what is going to be our dependent variable that we're trying to predict. We're calling those variables, we'll call them features. And then we use those features that we decide to include to build our model. We train and test it, and then we will validate it and optimize it. And then we might have to go back to rebuild it or modify the model until we're happy with it. And we continue that cycle until that we feel like the model is optimized, or we run out of time, and then we deploy it. So then we allow people to use that model. All right, so the first step that I want to talk about, I'm not going to really go into the cleaning and transforming data. That's going to be different for every data set that you use. But the next step in that cycle was the exploratory data analysis. And this is an important step that we have to understand our data before we can do anything with it. We have to know what data we want to use. So As part of the exploratory data analysis, we're going to, there's actually 3 steps as part of this. The first step is understanding the collection of data that we have. Maybe look at the number of observations in that data. Observations means the number of rows that we have in that data, the different features or fields in those rows. Maybe look at which of those features are identifying fields or descriptive fields. And then looking at the fields that are going to be probably most relevant to our study. So this is just a high level look at the data to see what data we have and what data we're going to really focus on or that are good candidate fields to use in our analysis. Then the next step is to look at the data actually as an aggregate then. So we're going to understand the properties for each of the relevant variables or each of the relevant fields that we want to use in our analysis. So this may mean conducting, figuring out the mean, median, standard deviation, or different quartile distributions for our quantitative values. It could be determining the data types that we're using, the formats for our data, looking at the number of null values, meaning that we don't have a value in some of our entries. And then also evaluate the distribution of our data, whether it be categorical data or quantitative data, see what the distribution of our values are. And then the final step is looking for relationships. So do we have relationships? Again, we're going to be focusing on predictive analytics. So we're trying to find variables that will allow us to predict the outcome of another variable. So there must be some type of relationship between the two. So what we want to do in this step 3 is to understand the correlations between potential relevant variables in our data set to see if one influences the other. So we're going to do some correlation, look at correlations between the two. And we can do these by building plots and observing correlations. There's also a correlation matrix that we can use. And then what we're going to do kind of as an outcome of step 3 is we're going to identify those variables that we want to include in our data model. All right. Before we go on, I want to just clarify, and I mentioned the word categorical or quantitative, and just kind of look at this hierarchy here of data types. So data types, data will be either categorical or numerical. And categorical data is further broken down into nominal or ordinal, and numerical data is either interval or racial. So, and part of this, like the most important thing is be able to differentiate between categorical, numerical, or quantitative. So nominal data, would be categories that really don't have any ordering function to them. So like I could say, this is a Lancia. That's a type of car. Or ordering categories. So again, categories, it's the name of a category, but there's some type of ranking or scaling of these categories. So some categories are rated higher than others, such as GPA or grades. So an A is better than a B plus is better than a C plus. So these are they're all labeled, those are categorical data, but there's some type of implied order to them. Next is looking at numeric data. And so one type of numeric data is going to be interval data. So this is an example would be like temperature, degrees Fahrenheit, degrees Celsius. There's no zero, absolute zero as an absence of data to it. We can have a zero that's a measure, but that's still, we have a value there. It's not a no temperature. And here, because there's actually no zero to it, we can calculate differences between values, but doing numeric, I guess more like multiplications or divisions, it really doesn't apply to this type of numeric data. Whereas ratio data, this would be things like maybe scores of a baseball game. Those are all, there's a zero and we can subtract, we can divide, we can multiply, create averages and so forth. And that's where we can do a lot of our numeric computations. So ratio data allows us to do a lot of things. Categorical data is where we're going to be looking at different categories, being able to classify data. So just know, I guess the key here is to know the difference between categorical and numerical data. And sometimes I'm going to call it quantitative data rather than numerical, but just that's probably the key here, because that's going to really help us determine which type of model we can use. All right, so exploratory data analysis. I'm going to go kind of walk you quickly through a couple steps here. Where step one here's where we can just look at our data. So here's a screenshot from R Studio. That's the interactive development environment for R that I use for R. And we can see that there's several fields here that I think are going to be relevant. This is game log, MLB game log data. So I'm taking a look at maybe the date of the game, what day of the week it took place, who was the home team, who was the visiting team, what was the visitor score, the home score, the number of outs that were required for the game, where the game was located at. So these are different fields that I feel were important, that might be important to an analysis of baseball games. Another thing at the bottom, you can see the number of columns. So I have 65 columns. That means 65 features. And I have 132,000 rows. And that's another thing. To do predictive analytics, we need lots of data. In the class I'm teaching, I ask the students to find data sources that have at least 500 observations. Anything less than that, your model is going to be a little suspect. So you do need lots of rows of data to be able to build effective predictive models. All right, so then next, once we see that the data, then what we can do is we can look at understanding the fields. So here's some code that I wrote in R. So what I'm going to do is I'm going to take a look at the year built, the sales price, and sold age for different homes so that I can understand kind of the range of data that I'm working with, or understand the data a little bit better. So here's the output. I can see for a year built, the oldest house was built in 1872. The most recent house was built in 2010. And the median value, the value in between, was 1972. And I can also see the quartile distribution, first quartile, the median, mean, and the third quartile. And then same thing for sales price. So this helps me better understand the types of data that I have. So I can see actually for sold age, there's an age of 0 in there as well. So that'll be important to understand. So I can get some information by just doing some of these summaries of my key variables. I also am going to be concerned about the distribution of those variables. And so what I can do is I can do a box and whisker plot, and this will show me the range of values and how they're distributed, or how the individual values are distributed. So here, the lot areas. So the size of the lot for all the homes that were for sale. And as you can see right here, this is a box and whisker. So the box represents the middle quartile, or the middle two quartiles of data. So that means half the data exists within the box, or half the range of data exists within the box. We have a little bit below it, and we have some data points that fall outside of this as well. But seeing that there's such a narrow spot of data here, this is kind of going to key me into something that I'm seeing a lot of data that's outside of the range here, and that line represents the upper quartile and low quartile, and then these are really outlier data. So I suspect I'm going to see something with the lot ranges that might affect my model. So looking at those outliers, I can do a histogram. And so what this is going to do is it's what we call a frequency distribution. So I can take a look at how often these values appear. And what I'm looking for is like what's called a bell curve, a normal distribution. And I can kind of see that a little bit. That's kind of extreme here. But I'm seeing there are outliers, so it is right-tailed, but there are some values, a couple of values in that stem way out here. So I'm seeing a lot of, so this means there are some lots that are quite large, that are much larger than most of my data. So I'm thinking that what I want to do is probably limit the data that I'm going to look at. And I have 132,000 rows, so I have some rows I can get rid of. So rather than trying to do a model on all of my data, I'm going to select maybe just part of my data set. I'm going to limit it so that model is going to be applied to maybe a certain subset of the data. So if I'm going to say I'm going to do a predictive model for homes that predict home prices for homes that are in neighborhoods. And let's say that most neighborhoods have houses on a half-acre lot or smaller. So if I narrow my data to half-acre, which means probably about here, right? That's a good way to narrow it down. So I'm saying my model's not going to apply for all homes, but only those homes that sit on a half an acre or less. I think I can get a better distribution of data. It removes all of my outliers, and I have a good business logic to get rid of some of my data. And I think I'm going to get much better results as a result of that. So then what I would do is I would go ahead and create a subset of my data that's only for homes that exist on a half an acre or less. All right, from there now, I can study my relationships. So taking a look at that lot size, I'm going to see if there's a relationship between the lot size and the sales price of the house. So here I'm doing a scatter plot where I'm looking at the lot size in terms of square feet. And as you can see, I did cut my data off to be half an acre or less, and the sales price. So we can see there, it's not going to be a great model, but there is certainly a relationship. You can see, visualize this linear relationship. If you put draw a line in here of kind of the center point of all the dots, you can see that it certainly does look like a linear relationship. So I would say that there's a candidate for this. I'm not saying that there is certainly a strong correlation, but I had something to pursue. As opposed to if you had dots scattered all over the place, that you didn't see any patterns to them, you would say probably that's not going to be something I would want to pursue. So part of our exploratory data analysis is to identify those variables that may contribute to a predictive model. So in this case, lot size is something I want to include in my predictive model. All right, so from there, we've selected our features. I'm certainly going to be using lot size. I could use other ones, but that lot size is one that I've found that's going to be, I think it's going to be a strong contributing factor to house price. And from there, with those features, I can go ahead and build a model. So what we're going to look at first is a regression model. And that's kind of what we're starting. This exploratory data analysis was specifically aimed for a regression model. What I tell my students, though, is exploratory data analysis is not it's not the same set of steps that you're going to execute every time you do a project. It's really aimed at the type of model that you anticipate building. So if I were going to be building a model for predicting home prices is a quantitative variable. Therefore, a regression model might be appropriate. So I'm trying to identify a number, and I can use the numeric data, such as lot size or interior square foot, so and so forth, different variables like that, to help predict what the price will be. So given that, and since I was looking at correlations, I'm thinking that there might be a linear relationship between them. So I'm going to look to build a linear regression model. So some examples of regression models would be exactly what we're doing. Predict a home price based on the lot size for properties of half an acre or less. But I could also build a linear regression model to predict ice cream sales based on the high temperature of the day. See if high temperature is going to be a good predictor for how much ice cream we're going to sell. We can possibly predict the number of poor mental health days based off of days of physical activity, or maybe even predict crop yields based on precipitation to that date. So these are different ways we can predict quantitative outcomes to our data. Again, regression models are going to be used to predict quantitative data. So if we take a look, another study would be taking a look at studying time and see if there's a relationship between study time and exam scores. And to be able to do that, and you've probably seen this back in your math classes, algebra, to be able to predict the line. If there's a linear regression, indicates that there's a linear relationship between the x variable, our study time, and the predictive variable, our exam score. We're going to say that if there is a linear relationship, we can just use the y equals mx plus b, that equation, to be able to predict y, our exam score. So that means there's a slope multiplied times the x value plus the y-intercept is going to give us what we anticipate the y value being. So here, we're going to say that in this case, what we're going to do is we're going to predict the exam score. We're going to say that exam score is going to be equal to the study time times the slope plus the y-intercept, plus if there's any error in there as well. And then with that equation, we can then predict what the values should be. So the red indicates the observed values. The line that we go through there, that is what we would anticipate what our predictions are. And we can see that we're pretty good with our model. We're right on target for a lot of these variables. Maybe at the middle end of this, but at the lower end, we're not quite so good. So this is still a good predictor. It's not going to be 100% accurate. As you can see, some of these values are off the line. So we're not going to be spot on all the time. So, and then of course we can, with those values, we can go and use that to be able to calculate our predictions. And then what we can do is then use those. So that was the labeled data that we have. And then we build our model, and we can apply that model to unlabeled data. And then given the hours, study hours, we can use our model to then predict what the score on the exam is going to be. So here's an example of, and this is what the output looks like. And this is going back to, this is a new exercise. So here I'm going to predict the car price based off of the size of engine, number of cubic centimeters. So I did this in R, and then this is the output. So when I summarize my model, this is the output that I get. So you can see here, I've developed a linear model where the formula is the price is going to be dependent upon the engine size, and I'm using training data to be able to train that model before I test it on my testing data. So it shows the coefficients. So this would be my y-intercept, negative 9687.88, and then the slope. And we can see that the p-values, which indicate our confidence intervals, they're below 0.05, which means we're going to be more than 95% confident that there actually is something that takes place. So in the statistics realm, we would establish a null hypothesis. That would indicate saying that there is no relationship between engine size and car price. Now, this p-value, which is below 0.05, means that we're 95% confident that the null hypothesis can be rejected. Therefore, there is a relationship between engine size and car price. That's what that p-value tells us. And we can see that right there. The other value that's important on here is the multiple R squared. So that's R squared of 0.8021. That indicates that there's that 80% of the variance, the change in value between engine sizes is going to be change in value of the car price is actually due to the engine size. It's not just randomness. So randomness may account for up to 20% of the changes, but 80% of the changes are a result of the change in engine size. And this actually tells us, first of all, if there's a positive correlation, then we get a positive multiple R. If it's a negative relationship, we'd see negative R. But that value closer to 1, as we get closer to 1 or negative 1, that means it's a stronger relationship, meaning that we're going to get more confident that the differences between car prices are actually due to engine sizes. So here, 80% variance, 80% of the variance is actually a really good model. So we're pretty satisfied that actually is engine size can be a predictor of car price. And then there we actually get our linear regression equation. So we can actually use that to apply that to unlabeled data to come up with what we think the car price would be. And again, that's our equation. Now, that was an example of linear regression with one variable. We can also do this, what's called multiple linear regression, where we're taking multiple variables to be able to build a linear model to predict our dependent variable. And so we could say that the study hours, this performance on quiz 1, and attendance, those are the variables that are going to predict our score for the exam. And again, we can do that in R. We're doing a multiple linear regression. We're saying that again, going back to the price of the car, we're saying that the price is going to be correlated to the curb weight and engine size and horsepower. And we used our training data. And here we can see that we have good confidence that the null hypothesis can be rejected. Therefore, there actually is a relationship. And the relationship is actually pretty strong. We're saying that about 84% of the variance is due to the changes in curb weight, engine size, and horsepower. So this is actually a slightly better model than just engine size. Engine size was pretty good, but this is even better. So that's how we would build a linear regression predictive model to be able to predict car price, either based on engine size, which we saw with our previous simple linear regression, or multiple linear regression, which is curb weight, engine size, and horsepower as predictors of car price. And then also keep in mind too, these are predictors. They're not 100% accurate. And that's always a good thing to remember when you're doing predictive analytics and your stakeholder group is interested in the results. You have to make sure that your stakeholders knows that this is not 100% accurate, just like your weather forecast, that the weather forecasters are not 100% accurate. They're giving you some likelihood based off of the models that they're working with. And that's what we're doing with these predictive models as well. So you're going to select a regression model when you're trying to predict quantitative values based off of quantitative variables. You have to be able to mathematically describe the relationship between the independent variable or that you're trying to predict and the dependent variables. Now, you'll have to make sure that you have sufficient observations or rows to build a regression model. And again, more is better. Next, we're going to move on to classification models. And we're going to brush through the remaining models a little bit faster. So classification models, this is where we're going to be predicting some type of categorical variable. Remember, again, the differences between categorical and quantitative or numerical values. We're going to predict a categorical value, such as the student's grade, based on performance on select assessments, or we could identify maybe fraudulent transactions, fraud or not fraud, which are categories, based on key customer attributes, or predict a patient's readmittance, yes or no, based on select treatments or patient attributes. So doing our classification models, we're predicting a categorical value. We wouldn't use classification models for some type of quantitative value unless we're going to create some type of pseudo classification for that quantitative numbers. So classification, we're trying to group the values into different groups and assign then those groups to some type of category. So some common methods for doing this would be logistical regression, decision trees, random forest, support vector machine, k-nearest neighbors, or naive binds. And all these are different ways in which we can do that, and you can kind of see the visual of how it works. But I think the point here is that there's different ways to be able to calculate or be able to predict. Now, logistic regression is going to give you a yes/no answer. So if you have fraud, not fraud, that's fine, or admit or readmit, that's fine. But if you have predicting what type of car, there's not more than two answers. So you wouldn't be able to do a logistic regression for that. But all these other methods apply. So these are 6 common classification models. And as part of doing a predictive analytics or predictive modeling for classification, you're probably not going to just select one. We can actually apply all 6 of these and see which model produces the best result, and you go with that model. So here's what one of the outputs are going to look like. After you build the model, you can build what are called confusion matrices to evaluate the goodness of this model. So we can say one thing we look at. So I guess before we go on here, I applied my classification model. I'm using 5 different classification models: logistic, decision tree, random forest, support vector machine, and k-nearest neighbor. So I'm applying these 5 models to predicting fraudulent transactions. So I have the data set, applied them to all 5 models, and here's what I get. First, I take a look at false positives. So here we're saying something was fraud, but in truth, it was not fraud. So our model's saying there was fraud there when there actually wasn't fraud. So this would be this is something we really want to get near 0. And you can see 4 out of my 5 models did get this right. None of them, only k-nearest neighbor had a prediction, one prediction that it said it was fraud when it actually wasn't fraud. So that's good. So 4 of our models pass that part of the confusion matrix. Next, we take a look at missed fraud. How many instances did we say that it was not fraud when it was actually fraud? So here we can see logistic regression model. There were 18 instances where it said that it was not fraud when it actually was. 72 for decision tree, 47 for random forest, but only 16 for support vector machine. So support vector machine looks probably like our best model because there's only 16 instances where it missed the fraud, but it did not have any false positives. So as you can see, we're going to get different results based off of the different classification models. And then we can just pick which model best is going to best work with our data set. And that's where we use support vector machine for this then. So that's example here. Fraud would be a yes, no. So it's a type of classification. We apply these 5 models, and this is the output that we get for predicting our data. So classification models, again, used for predicting categorical values based off of our variables. We have to make sure that we do have enough factors or contributing variables to make this result. And again, observations, we want to have as many rows as possible. Survival models, these are going to be used to predict a survival time, maybe for a patient receiving treatment, maybe predict if a hotel's reservations can be canceled based on the date or the distance of the date from the reservation was made, or maybe even predicting employee attrition. So really, this is taking a look at what's called a time to event. So patient passes, patient comes down with an illness, a hotel reservation cancels. Those are all different events, and we're looking at the probability, kind of the probability timeline of that event taking place. So we have a period of time, and then there's some type of event from the starting event to the point of our kind of variable changes. A patient is healthy all the way till event 2, where the patient falls sick. So that variable changes at event 2, and we're trying to predict what that duration will be, and the probability of that event 2 taking place at any time point during the timeline. So survival really is looking at timelines. So, and here's the Kaplan-Meier plot, which is common to a common output for survival models. And this one shows 2 different data sets. One is a group of patients that has had prior heart surgery, and then the group without prior heart surgery. And this is their survival over time. And you can see at the beginning, 100% survival, and then you can see around at 80%, we have 80% of the without prior heart surgery at this point in time. And we can see about 60% the survival of 60% of our population surviving maybe at 75 days without, but really it doesn't fall until about 1,000 days for those that had heart surgery. So this shows the length of time to event, and this is survival. So this is if they pass for one group compared to another group. And then the probability at any point in time, that's what the line's measuring. Then we can also use this hazard ratio to show which of those variables are going to be strong contributors. So if I did a survival analysis on employee retention and found with the data set that I was using, I see that, and I'm taking a look at these p-values showing that those employees that travel frequently are much more likely to leave the company earlier than those that don't travel. Gender compared to females, males are going to be slightly more inclined to leave the company. Marital status, divorced, there's not a lot of difference because of the range of values, divorced versus married. But if you are single, you're much more likely to leave the company. So these would help us indicate those factors that are going to influence that event, whether that be death, whether that be hotel cancellation, whether that be leaving the company. These would be showing this hazard ratio was going to show us the factors that influence that event the most. So these would be, then the action would be to try to mitigate these, or to try to have programs or such that if it's something that we're trying to avoid, that we can to mitigate the result here. So again, this is looking to predict an unchanged categorical status over a period of time. We want to make sure we have enough factors and enough observations to be able to do this. So that's what our survival model. And our final model is time series. And this is probably what you're familiar with by watching the weather. This would be a time series type of model where we're going to predict either stock prices, maybe product sales at a certain point of time, or maybe high temperatures. So we're all this data is you're taking data that's continually measured over time and predicting what future measures are going to be, such as international visitors to Australia. So we can see that we've tracked over that time, and then based off of that data, we're going to predict new values. But you can see that you can build a lot of different models, and they're going to give you a lot of different answers. So again, it's not perfect. And there's four main models out there for time series: ARIMA, SARIMA, VAR, and LSTM. LSTM and
Brandon,
VAR, yes.
sorry to interrupt, but I'm not seeing your slides right now. I don't know if you accidentally stopped sharing or if
Oh,
you were just moving off of those.
let me try this again. Sorry about that. Thanks for catching that. And can you see that?
Yep, we're good again. Thank
Okay.
you.
Yeah, sure. So these are the most common forms of time series models, where LSTM and VAR, they're going to be more machine learning. So in our predictive class, we focus on ARIMA and SARIMA models. But basically, it's taking a time series. So that means data that's collected either daily or weekly, but or hourly on a consistent basis. And we need at least a year's worth of data to be able to predict the future. And the further you go out from the future, the harder it is to predict. Um, so here's an example where I was taking a look at 4 different locations and trying to predict the number of vehicles per day. This 4th location didn't have a year's worth of data, so we can't use that in our data model, where the other ones can. And really what we're looking for is an overall trend that helps us with our effectiveness. And if there's any cycles, like maybe during certain times of the day, it's going to be busier, or maybe like if you're looking at temperature, for some reason we have warmer temperatures in the summer than we do in the winter, that would be a good cycle that we're looking for as well. And then we can take a look at that plot over time. What are the values? And you can see that first data set probably would be the most valuable, but it fluctuates so much, it's not going to be a good model. So as a result, you're going to get results like this that really, it's difficult to predict. You really can't, we don't have the right type of data or the right patterns in our data to predict. So here's what an example of a poor model, or the data is poorly designed or poorly fits a time series model. But time series does require consistent measures. So we're going to predict quantitative values over a period of time based on past measures and past cycles. There should be cycles as part of that. So we do need enough factors and enough observations to be able to use this model. So again, we looked at regression, classification, survival, and time series. Those are the most common forms of predictive analytics. But we started off by looking at the different forms of analytics and the questions that we would ask. Descriptive, meaning what happened; diagnostic, of why did it happen; and those answers help us to then go into a predictive study of what will happen. We know that there's the difference between supervised and unsupervised data. For predictive modeling, we're going to use supervised data to be able to build the model. And then from there, we can apply that model to unsupervised data to be able to predict that outcome variable. Whereas machine learning can be used on unsupervised data to build models from there. And again, the regression, classification, survival, and time series. Those are the most common forms of predictive analytics. So I know this was a lot of stuff that I threw at you over an hour, not expecting you to know how to do it, but hopefully you have an appreciation of how predictive analytics works. There are limitations to it, and these are estimates, and then the type of questions that it's going to answer, and how the answers to those questions can be valuable. And this is the process that we follow, again, noting that exploratory data analysis is key, and data cleaning and transformation does take up a lot of time. So we still have some time here for questions or comments. Any questions about how you would use this, or comments on your experience with predictive analytics?
Feel free to type those in the chat too if you don't want to come off of mute.
I know the biggest thing that I've always found with working with this data and when I was going through the certificate program was knowing exactly what you want to try to find out so that you can choose the know what information to pull out from your data, and as you were going through all those models, exactly what model you want to use and how you want to get there, sort of thing.
Yeah, that is key. You have to know, and that's why it's important to understand before you do any form of analytics, you need to understand what problem are you trying to solve, because analytics is supposed to provide you some type of action-oriented response. So what type of problem you're trying to solve, or what are you trying to solve? And then from there, you come up with the questions of what if I answer these questions from my data, I could come up with a solution. So you kind of need to establish, that's the groundwork that you need to establish first. And then really knowing your data, that's why we do exploratory data analysis. We can see what data we have, and based off of what our predictive, what our dependent variable is and the independent variables that we have access to, and the type of questions that we're going to answer, that will help us figure out our model that we want to use. Time series is certainly different than survival, which is different than classification or regression. So they all serve different purposes. So it's a good idea to first have an understanding of those, maybe at least those 4 types, so that you know the type of questions you can answer. But thanks for the comment.
Question in the chat there, Brandon.
Get to that. What tips or tools would you suggest for folks who may not have mathematical background and want to integrate these methods and tools in their roles? You develop some of this language and the analytic or the statistical methods in language as you go. Good Google searches, AI tools can help you explain some of these concepts to you. To be able to do predictive analytics, you're not going to do that in Excel. Yes, you can do a linear regression model in Excel. It's prone for errors, and it takes a lot more work. I'm going to be biased. I think R is a great way to use that. So download R, and then the interactive development environment is RStudio. Download that and install it after you install R. Both of those tools are free. And that allows you to be able to do this type of analysis. They are scripting language, so there's a steep learning curve. So it does take a lot of effort to get there, but that's a good way to get started, is take a look at that. And then like that screen that you saw for my linear regression, it had a bunch of statistical language in there. Then what you do is you get that, look at the results, Google what everything means, and that's going to help you learn along the way. That's what I did. I started from 0 as well. But thanks for the question, Jessica. All right, last call for questions. All right, so if you want to, you can contact Eric to get a copy of the recording. If you want the slide deck, you can just use the QR code here and be able to download a PDF version of the slide deck. And feel free to connect with me over LinkedIn, or I've got a Twitter account that I use sometimes. And I typically would post information about other presentations that I'm doing. So it might be a reason to follow me on either of those social media platforms. But thank you for coming today. Appreciate that. And I hope you got an appreciation for predictive analytics and what it can do. Thank you.
And thank you, Brandon, and we'll get the email out with the follow-up video and other things. So have a good rest of your day, everyone.
Thank you. Bye.